are some of the designs that the students have made. Okay, this was the last thing we talked about. The main thing that uses the omni-wheel can move in both directions. So if like in one direction it will move, the other direction will slide right. And the main task is to like make every colony sites whether they are like have damage or not with the LED that's present in the board. These are some of the designs about the students. This is the arena tracking simulator. Yeah, the hardware, right? So let's dive into the topic of like control system. So before going to control system, I would like to emphasize like what do you mean by a system? So any idea like what do you mean by like a system means? What system means actually? You can give your answer in the chat. Okay, so according to me, the system is like the group. Yeah, I got an answer. I think group of interconnection of elements. So that's the correct answer. So it's like a group of components or devices or that are like meant to work together to perform some task. So that's the system, right? So here we'll be dealing with the control system. So it's like a system which has some controlled objectives. So what do you, any vague idea about like what do you mean by a control system? How system is differ from control system? Any idea? Okay, so I think my slide is visible, right?
Yes, it is visible.
Yes, sir,
Okay.
it's room.
Yeah, okay. So the control system. So what do you mean by a control system? Any idea? Vague idea? So the system which has some controller on it to like make the system to do its own or like some task assigned to it. So if you see some example, we can like have some example like car. So basically the car is a kind of a system actually because it has like so many components, right? And that components are like work together to do some task. So if you want to make that car as an autonomous, then we'll be like having some kind of sensor to like check whether any how the environment is there and any obstacles or any passenger or any human beings or anyone is there. So basically we are trying to implement something to make it like more controlled and also making it autonomous. So there are like two classification of control system, like basic systems. So any idea about like what are the classification of control system? The main classification. Okay.
Sir, wired control system, wireless.
Yeah. Yeah. So kind of like basically the main classification is about like open loop and closed loop. So like what do you mean by like open loop, closed loop? Any like idea? What? Okay, so the open loop system is like you'll be giving an input to some like controller element, and that controller element will give you some controller output to the plan. The plan can be anything like a kind of a car, motor. For example, if you consider a motor, so you're giving some PWM and it's rotating and it's giving some output. According to the PWM, it will give you the varying speed. That's all. But in case of a closed loop system, yeah, so we will take the feedback from the output. So why this is required? So if you see, for example, just consider an example like you're having an air conditioner in a room. So if you're just applying the open loop system concept in the air conditioner, assuming that the air conditioner is not having the feedback of the temperature. So you'll be just measuring the volume or the size of the room, and you will be giving the control input such a manner that the temperature is maintained in for example like 25 degrees Celsius. If you want to keep it, will just keep on, like we'll say like on for some duration of time, then off for some duration of time, just like a normal on turn on and off concept. But just consider there might be some uncertainty. For example, we might not have like measured properly the room size, or like there is a window or something where the uh, air conditioners, the regulation will face, because the due to the opening there will be like a what is it, the particular temperature cannot be maintained. But in if you have a feedback in this case, so if you are like, even though your model is not correct, for example the volume that you measured is not correct also, it will uh, because we are having the feedback, so based on the feedback it will take the output and we'll have the reference. For example, 25 degrees Celsius is a reference, and what's the current output of the current output, means the current temperature of the room. So it will take both into consideration, and it will give the like it will take the negation of both, like input minus the output, which is the error. So our main objective is to like minimize the error to zero, right? So this is given to the controller, and based on the error, it will give you the control input to the plan, and thus that way the uncertainty that might be there in the plan model can be like removed. Okay. So have you come across like any controller before? Like what do you mean by controller? Okay. So just in terms of control system, it's mostly not related to the microcontroller. It's related to the controller algorithm. There are like so many algorithms are there, but in this session we'll be focusing on the PID controller. Okay. Also, you can see a block named as feedback, and that feedback you can get it like nothing but the sensor element. Okay, let's dive into the like the main thing. So I've told you about the PID controller, right? So this PID controller, if you can see some similarities between the closed loop controller block that I showed you. Yeah, here the closed loop system where there's an input and there is a controller plan and a feedback. The same thing if you see over here, yeah, there's an input named as R of t and output y of t, and R of t minus y of t will give you the error, and this error is given to the PID. So this PID stands for proportional integral derivative. So we will be discussing about this in a very brief manner. So this controller will be like the summation of this thing gives you the controller output, which is termed as like U of t. Uh, I would like to like um, yeah. Now keep into error plus it's actually AI. So this KP AI, uh, yeah, you can see the code. Like KP AI KD. So these are the corresponding like PID constants will be like multiplied to the system. And the okay, and the error is like proportional term is only having the and integral term is having the summation of error, which is like error term. And derivative the name itself is subsequent term. Derivative term is having the rate of the error with respect to time. So the error is changing with respect to time. Yeah. Okay. So the equation is Kp into error, Kp into integral of the error plus the Kd into derivative of the error. So, so first we are going to see about only the Kp into error. So if you see here, I'm considering there's only the control is there
Hello.
for now.
One second, Jayesh. Can everyone else mute themselves, please?
Uh, if you have anything to like say, you can just put it in the chat actually. Okay. Yeah. So for now, first we are going to consider only the proportional controller. So how it works. So if you see this u of t is like proportional to the error. So if you are having a just this is like a input. So this is the desired output. Just consider this is the desired output that we want. But our system is like initially in the origin, just zero. So what it does is like if you consider the error, so error we know, right? So input, so r of t minus y of t. So this becomes the error. So just r of t is the desired value. So this is the r of t, and y of t will be the current output. So this current output is 0, then this is having some value. So due to the difference in this value, so the error, initially the error value will be very high. And as it like approaches, so it will try to go towards the correct error. So we have already said the thing is like the control system, the main aim is to like make the error to the 0. So the error will try to go in. But what happens is like as it goes near the error term, value will become very less. So for example, if you consider a motor, so in that case, you need a certain there's a threshold level. So below which the motor won't rotate. So for example, some motor won't rotate below like 50 PWM. So in this case also it might happen. So it will go forever, but as it reaches the error value, so what happens is like it can't able to give like because the error term become less and the PWM value might go below that. So it can't give. So it will try to balance or they like try to maintain the state in the same way. So it will try to maintain in this range. So but still this is not the required, and because we are having an offset. So do you know the what there's a name for this offset which is called as like steady state error, because there is a steady like a constant offset is there. Okay, so now we need to eliminate this. So this in order to do that, we require integral. So what integral does is like it will just sum up every error. So already we have like kp into error. So now we are just introducing the integral term ki into the summation of error. So what it does is like, so previously our error, because if you see in this particular graph, you can see there is a constant error, but the error is like a constant. But in case of this integral, what it does is like it will accumulate error. The value of this, the actuator or the output will try to increase because the error is getting accumulated. So this will push this particular output to the desired location. But still, we might have like some kind of oscillation and like we might reach this thing. But in some cases, this oscillation is like a very critical thing and it's like a very non-desired thing. For example, you can consider a kind of just a sudden if you're driving a car and it's like a sudden jerk due to the like kind of a sudden vehicle pass, it's not a desired one. So we need to just predict that. So we need to predict, okay, something is going to come in your way. So something is going to come in your way and you need to just prevent that. So that part is actually taken care by the derivative part. So what derivative does is like it will just determine. So if you see the derivative term, yeah. So this derivative term, what it does is like, so it will change according. For example, if your error is for your current error is like, if you see here, this error is like going very fast. I mean, the very fast and trying to get the. But the derivative part, what it does is like, so if the error part is like, this is the current error and this is the final. So it will take the current error as well as the previous error. So how fastly the error is going to vary. So for example, as it reaches here, it knows like the previous error was like less than the current error. So it will try to reduce the effect of the P controller, and thereby it's like reducing the oscillation caused by the PI controller. So previously the output was like kind of oscillatory motion, but it settles. Now what it does is like it will reduces the oscillation to some extent. But if you're having a good tuning of these three parameters, you will get a good like a smooth curve. But ideally, it's like a very difficult thing. So you'll have some oscillation, but it's like a okay workable case. Okay. So this is how the PID works. Yeah, I would like to show you one of the like graphical representation. Yeah, so this is for a system. So first, like we are increasing the KP, you can see that there's a it's trying to move towards the final desired location, but it was not able to do that. As a P increases, you can see there is an like an oscillation also getting increased. So now we are like increasing the integral term. So you can see that the output is like reaching towards the desired output that we want. But still the oscillation remains the same. You can see there's still oscillation. Now we are introducing the KD term. Yeah. So the KD term removes the oscillation and you are getting a smooth curve. So yeah, this is how the PID, like the tuning is like usually like done in the observation based tuning method. Yeah, this is one of the graph, the same graph, but it's like just a normal thing. Needs the steady state was like the desired location was 1, but it was like initially it was like having in 0.8. It was having steady state error. So let's see about the advantages and
Hi Dion,
disadvantages
how
of.
are you?
I think I can hear some sound. Can you mute? Uh, okay. So the advantages of the PID is like there is no need for like a model. There are like model based control for PID, but in most of the case, like without the model also we can just do it by just by observation. We can do the tuning and like we can get a desired value that we want. And also like the thing is like we need uh, even though the modeling is like not perfect and like there is some uncertainty, this will take care of that. Like there's no need for model, but still. And the disadvantages if you see, since we are like not considering into the model, so it's basically if you see the observation method is like mostly by hit and trial. So for some system it's like very easy to tune, and for some system it become very difficult in tuning the three parameter because there are like three parameters. So in real life, the three parameters like varying one parameter will affect the other parameters affect that is caused previously. So if you are like tuning like P, I, and D, like and then second time like if you are like trying to just change the derivative part, it will have some more effect on like proportion like the P control P side. So we need to actually tune the P as well. So P by varying P, then we need to think I. So it's like you need to tune the three parameters. And also the main thing is like the system. We are not sure whether the system is controllable or not. If we know the model of the system, we can judge like okay, based there are like some methods in which we can analysis where the based like the with the given actuator or like with the given uh, inputs, the states can be uh, reached or may reach to the desired location. Since we don't have the model, we don't consider the model here, so we are not sure whether it's like controllable or not. So it's like uh, we are not sure whether controllable or not, and we are trying to control it. So what the system is not controllable, even though we are sitting and doing the control for like 2 days, 3 or 1 month, it won't work because the system itself is like inherently it may be sometimes like non-controllable. Okay. Yeah. Yeah. Next is like I've told you about the simulator that we use. So the name of the simulator is the CoppeliaSim. So this CoppeliaSim is like we can use the Python scripting for like program this uh, platform, and in this we can create our own model as well as like if there are like some example models present over here. So I would like to show you the some of like how to work with the CoppeliaSim and like how the CoppeliaSim interaction will be. Just give me a second. I'll join my system. Yeah, I hope hope my system is like visible. Yeah. So this is how the CoppeliaSim looks like. So you can see, like I've told you, like there are like models you can see, like inbuilt models. So these are some inbuilt models. You can just work with it, and you can see scripting also, how it's like written in the scripting, so that you can just explore it yourself. So for exploring purpose, you can use the user manual. Yeah, it's like a very well documented like user manual that you have. So you can just go through the overview and just go through the like what are the things are present, and also like what you mean by like a scene, and you can see some tutorials also. So this is not the scope of like this session. So I'll be just saying like how to like make some like simple shapes kind of. Okay, so I have made this shape. So this is a cuboid that you can see. Yeah, so this cuboid is like a parent for this, like there's a hierarchy you can see. We call it as like parent child hierarchy. So this cuboid is like a parent of revolute joint, and the revolute joint is the parent of the cylinder. So you can just change the hierarchy also if you want, but I made this hierarchy in such a way that so the cuboid, the revolute joint should be like attached to the cuboid, but whenever this, so I hope like how the joint works. So there are like three types of joints. So for getting this, you can just right click on here, and you can see like primitive shapes, where you can see like so many shapes that we have used, like cuboid, cylinder, and so on, and that you can explore this. And there are like three types of joint, and and there are like three types of joints: revolute joint, prismatic joint, and spherical joint. So the revolute joint will make the object revolute around its axis. Okay, so I've used this joint to make this particular shape. So okay, so if and there are like dynamics of the joint. So the dynamics may be like free. So in free joint, it's like the joint won't do anything. Like even though we are giving velocity or anything, it will just keep on. It will be in the stationary position, so that you can just explore by installing the this particular simulator. Okay, yeah, and you can use the API. Uh, yeah, so if I'm running, I think you can see the it's yes rotating. So if I want to change the direction, just I can uh, also before that I need to say something about. So you can see there are like so many like objects out there, like cuboid, revolute joint, and cylinder. So this everything are having their own unique ID. So in order to get that unique ID, there is like an API called like sim dot, and you need to just write the name of the whatever objects that you have, like what you want to. So it is called as like object handle. So it will be an integer. So for cuboid, it's like 15. And if you see for like the other thing like revolute join, oh, you will have like the different. So it's like a case sensitive. So it should be clearly it should be mentioned like okay. So you can see a different ID. So this is called like object handle, which is nothing but the object's ID. So why I'm like saying about like this object ID kind of thing, let's see. So for example, if I want to publish or like if I want to give a velocity to the joint, to the revolute joint, so there's other API which is named as So you can use like tab to the auto completion. So this is like a, so what this API does is like we have a joint and it will give some velocity, whatever velocity integer that we are giving, it will give that, publish that particular integer like velocity to that particular join. So I'm just giving, we know that the Revolut joins object handle, but you can see it here also what are the things it's required. Yeah, so you can see that the particular API requires like object handle and target velocity and the motion param, that's like without that also it's like an optional argument. So let's start. So 16 comma, so I'm giving like 1. So it's like rotating in the same direction. Okay, I think there's a, okay, the script is being run. That's okay. So okay. Yeah. So like the same thing you can do it using the script actually. So this script is called like child script. So it's written in Python. So here we will be having a, you need to declare the global values that you want. So I'm declaring that object handle, which is like an integer over here, like the Revolut join, and I'm getting the, and like this syscall init function will be like calling only once for initializing purpose, and this actuation function you can use it for like giving target velocity to the any joints or like to some other wheels or something. And syscall sensing where you can like, there's other APIs which can be used for getting the orientation, position, and other stuff like uh, making it like for for example, if you want to, in case of like you want to calculate error from the position, everything can be done using the sense like syscall sensing function and the cleanup function. So let's see like how the function is being worked. So I'm just making it like -1. So you can see it's rotating in the anti-clockwise direction. Now you can see it's like rotating in clockwise direction. It changes its direction. It's running using the script. So I'll just reduce this. Yeah. So I'll just try to, now I've removed down. Yeah, I think you can see that it's changing the direction based on the uh, sign that we are assigning to the target velocity. Okay. Now I need to like, I like to come back to the slide. So this is how the overview of the how the simulator looks like. So I told you like we can make some like complex shape using the primitive shapes that I've showed you. So this is one of the examples. So this is the cart inverted cart pendulum. Okay. So it's, you can say that it's trying to balance without making the pendulum fall. It's like moving in the to and fro direction to make it upright almost. Yeah, I think now I've given you a glimpse of like how the control system and like what are things you're be using. So the simulator that I showed, which we'll be using in the uh, control system theme for the stage one purpose. So there you will be like designing everything that you will be doing in the stage two hardware part in the simulator. So now it's like time to like see about like what's the scope of like a control system. So any like there are like several yeah there are like several applications of the control system. So these are like a very few handful of controls. So if you see the board that is done, it's like done by Boston Dynamics. So you can see like even for like just to make it stand upright and just walk, you need like a many controller, right? So it's like it's having like so many actuators also. So it's like if you're going with like a PID controller, so you need to have like that much amount of like that much number of PIDs you need to have. So and you, for each PID there will be like a kind of or you need to tune. So it's like very uh, hectic process of like tuning the PID. So there is a like other and you can see the other things also like the bot the which is like the four-wheel quadruped. So it's like that maneuvering is also not a very simple PID thing. So in team we will be like introducing a new controller like called which is like an optimal controller called LQR linear quadratic controller. So that you will be that's not a part of this session that you can learn in the team. So these are some of the things like autonomous car is also part of the conversion because it's like takes some sensor and it's like um, it's trying to respond to the environment. Okay, and this is the overall map of the control system. And the thing that's mentioned, like the mark with encircled with red color, like what are the things that you'll be learning in the team. So you'll be learning about like LPR, and you can see like here is the. So there are like so many untouched portions also there. So by learning the basics of this, what are things that you have been learning, so you can self-learn the other like other things that you can see in the control system map on self. Basically, you can do the self-learning of the remaining things. So I think yeah, that's the. So if you have any question, you can just put it in the chat. So yeah, thank you. Do you guys have any question? Uh, any any questions? Like any doubts regarding the any topics covered or anything?
No, sir.
Okay. So I hope like there are like no questions. So I'd like to say something about like yours. So the registrations are like still August 25th. You have the registration. So I'd like to show. Yeah.
Sir, I got something to ask about the registration.
Yeah.
So the whole image processing technical session, would that be in a person-to-person interaction, something like that, or would it be a live session?
No, it will be person to person, but it will happen in quarter, I think.
Okay, so actually, I wanted to attend that, but unfortunately, it's not showing up on the portal like that session. So should
I think the session is today. I think you can attend.
yeah, it's today at 2 p.m. 5.
Just a
So
second.
yeah.
So there is an image processing session is scheduled at Kottayam at 2 p.m. So you can attend that. There is no need of registration. You can go on spot and do the registration and attend the image processing session.
But thank you, thank you.
Do you know the location, the college name?
Yes, yes, I'm actually a student of the college.
Yeah, okay.
Okay, thank you.
Okay. So anything else? So this year's I'd like to talk something about like this year's theme. So this time there are like 4 themes are there. So logistics cobot, balancing builder bot, commander bot, and warehouse drone. So the logistic cobot is mainly about the industrial manipulator. Yeah, you can learn these technology stacks that's mentioned like ROS2, Gazebo, computer vision, and like it's mostly about like you'll be working on the remote hardware, which is like a industry manipulator, UR5 arm. So you can see here UR5 arm. So these are the system requirements that you can go through. And the control system theme is, which is like a balancing builder board. So in that you can learn about the yeah. So you if you have gone through the paragraph, so you can see like in this we'll be like building a balancing board with a manipulator. So it will have a arm kind of structure which will be used for like pick and place or like carrying objects from one place to other. So the main thing you'll be learning is like doing is like you need to balance the board as well as like traversing, and you need to maintain the upright position while balancing. And these are the technology stacks that you'll be learning, like 3D designing of the bot as well as the manipulator, and Python for like doing the simulation part, and embedded system. Like the in task 2, you'll be doing the hardware implementation, and control system concept. Obviously, it will be there. And these are system requirements. And equipment robot is like a you'll be using FPGA for like doing the problem statement that's stated here. This is also basically the implementation is both simulator as well as hardware. So in stage 1 you will be using the simulator, and in stage 2 hardware. And last is like the warehouse drone. So it's about you'll be using the drone, and the technology stacks will be like the same as more or less same to the logistic bot, but the thing is like you'll be working with the hardware drone in the stage 2. So it also has the technology stacks like ROS2, Gazebo, and so on. So only like 4 days and 17 hours are like left for the registration. So whoever like not have registered or like interested in like registering, you still have the time to register. Yeah, you can go through the portal like portal.e-yantra.org and you can see the register here and you can register if you're like interested in like any of the themes there. And also you can go through the previous themes also, like how the previous themes were. So these are the videos of the previous year themes. You can just see like filter using like which year you want. Like this is like exactly the last year ka theme, like a drone, color board. This is like the same the UR5 the warehouse management using the manipulator. So this is the yes, this yeah, yeah, these are the participant build board. So it's like traversing the obstacles. The patches that you're seeing are like the obstacles. So you'll be like learning the concepts like what you have learned, but in some kind of different systems. Like only the system differs, but the concept remains the same. Yeah. Do you guys need to know anything else? Do you have any doubt or like any query regarding the UIRC or anything?
No doubt, sir.
Okay. Oh, so can we wrap up the session? Okay.
Sir, is there anything feedback form we need to fill here for attendance?
Sorry.
Is there any feedback form or any attendance that we need to fill?
No need.
Not needed, right?
Yeah, it's not needed.
In the chat box, in the afternoon session, which is scheduled in the different location of India, like in Mumbai, it is in Vidya Vihar.
Okay.
Shall we need to go there physically?
Sorry.
Hello, sir. Shall we need to go physically there?
So, can't hear you, sir. Please, can you repeat your question, sir? Query.
Sir, my question is that as I attended this morning session here on online, and there is the afternoon session also, right? That is
Yes, yes.
take vision that
Yeah, sir. You have to go there, sir. In KJ Somaya, you have to come to KJ Somaya. Our team will be taking that session.
Mumbai. Yeah.
Yes, yes, yes.
Okay, so shall we need to come there physically?
Yes, yes, yes. In the physically,
आना
that
पड़ेगा
is
sir.
that is the physical sessions. Like you have to come there, and our team will be there to give that session.
Along with student, can we come?
Yes, yes. Along with the student, you can come, sir.
Because this year participation, the students are also registered for EYRC 2024. Now,
Okay.
now afterwards, what I am asking ki, being a faculty and ELSI coordinator in my campus, shall we need to come there physically?
Sir, if you are interested, then you can come for the session. It is not as a compulsory. If the student are interested and you are interested, you can come for that session.
Okay, sir. Then we'll decide because my load is there. We need to compensate many things, no?
Yes, yes, yes. It
So
is not
what
a compulsory. It is just that teachers competition ka finale bhi hai. So and we are along with that we are taking that extra session. So whoever interested, they can come to that session.
We'll send students, sir. They are
Yes,
interested to check the teacher's project,
yes,
and
yes,
we'll
yes,
attend
yes.
online, sir. Thank you, sir.
No issues. They can come directly to the session.
and the attendance certificate will be there for everyone,
Yes,
those
yes.
who are
That
attending.
after the attendance, we are taking the attendance there, and then within next 2-3 days, we will give the attendance certificate. Whoever present at that session.
Only physical presence, right?
Yeah, yeah. Only physical participation for that.
Okay.
Yeah. So can we conclude this session? Anybody have any another query about regarding UIRC? Okay, good. Then we will conclude this session. See you in the afternoon session at KJ Somaya.